All right, so let's get back to some useful chemical reactions. In the chapter 8, we actually discussed the radical addition of HBr to carbon-carbon double bonds. We didn't go into any detail for that mechanism at the time. I'm sorry, maybe it was in, chapter 9, not chapter 8. But now we're going to go in and discuss this reaction in a little bit more detail. We did learn that that reaction with the double bond gave us the anti-Markovnikov regioselectivity, right? Where the bromine reacted at the less substituted carbon of the carbon-carbon double bond. Right? So if we look at HBr addition, if we don't have any peroxide added, it's going to add via a, via the typical addition in the Markovnikov way, where we have the bromine adding at the more substituted position and the hydrogen at the least substituted position. Whereas what we talked about earlier is if you take HBr and you react it with a peroxide, and under peroxide conditions, the hydrogen adds at the more substituted position and the bromine is at the least substituted position. And so this anti-Markovnikov addition works very well, 95% yield for this particular reaction. But the key here, the key difference is one works without peroxides, the other one works with peroxides. And the key difference, again, is we get a radical mechanism of addition when we have a peroxide present. So the overall mechanism, the arrow pushing, is going to look very, very different. So like all the other mechanisms via radical pathways that we talked about, the first step is initiation. Right? We have a thermal homolysis of the peroxide that initiates the formation of a bromine radical from HBr. Right? So we take the peroxide, we heat it up, right? We get a homolytic cleavage. All that means is we split evenly down the oxygen-oxygen bond to generate two peroxy radicals. This cost energy, right? We added heat. The delta H of this reaction is 151 kilojoules per mole added to the reaction. The second step is, right, one of these peroxy radicals then reacts with the HBr via a single electron reaction mechanism, right? We have the OH bond that's formed where one of the electrons from the HBr bond goes and forms the bond between the oxygen and hydrogen. The other one forms the bromine radical, right? This is a hydrogen abstraction step, right? The peroxy radical is abstracting the hydrogen. And you can see this bromine radical that's generated is now created and able to move on to the next propagation steps. And again, this process actually releases 63 kilojoules per mole. Right? So the overall initiation step requires energy to be added, as you can see if you were to sum both of these up, in order to get the reaction started. So now if we take a look at the propagation steps, the bromine radical that was produced via the initiation step, in theory, could add to then either side of the alkene, right? So we have an alkene drawn here. If it adds to the left-hand side, we draw this structure here on the left, right? We have a radical there. If it adds to the right-hand side, right, we generate a radical here. And you can see, obviously, the radical that's in the molecule on the left-hand side is a tertiary radical. And as we discussed, just like with carbocations, tertiary radicals are more stable than the secondary radical that is generated here in the right-hand molecule. Right? It's less stable, so therefore not formed. So you can see we get selectivity for the radical addition to the less substituted carbon. Right? So this carbon, the less substituted carbon, is where the bromine adds, and it's because of the fact that we generate the tertiary radical along the way. propagation continues where the bromine radical now adds to the less substituted of the alkene, generating the more stable or more substituted carbon radical, right? So this is just showing the exact reaction mechanism from the previous slide and eliminating the secondary radical that we drew up above, because only the tertiary radical is generated, right? That process releases 13 kilojoules per mole of energy. Well, this radical then reacts with another molecule of HBr, as shown down below. When it reacts with the HBr, another hydrogen abstraction process occurs, and that hydrogen abstraction process regenerates the bromine radical, which can then again continue the reaction overall. And you can see the overall anti-Markovnikov addition that occurs across the carbon-carbon double bond. This second step, the hydrogen abstraction step, also releases energy in 25 kilojoules per mole. So the combined two steps for propagation are exothermic and releasing energy, so therefore very favorable. So this reaction occurs very, very quickly in comparison to many other types of chemical reactions. So our termination steps look again very similar to terminations from any of the previous radical reactions. Usually the radicals that are in solution are going to be bromine radicals. So the most typical termination step for this reaction process is the coming together or the coupling of two bromine radicals to form Br2, right? This destroys the two bromine radicals, and therefore neither of these two are able to continue the propagation steps shown on the previous slide. But overall, you could draw any of the two radicals that are present in solution at any point in time coming together as a termination step for the overall process. So up till now, we've been discussing this anti-Markovnikov radical addition of HBr to the carbon-carbon double bond. And the reason for that is it's generally a spontaneous reaction, and which basically means that the products are favored in the reaction pathway. Unfortunately, the radical addition of HCl and HI are typically not spontaneous, which means they're reactant favored. Let's take a look at the free energy equation here and compare the free energies of each of these, the thermodynamics of each of these additions, to get a better understanding as to why HCl and HI don't add very well across the carbon-carbon double bonds, whereas HBr works extremely well in this process. So when we step back and look at the first propagation step of the addition of the halogen to the alkene, right? First propagation step, the radical reacts in a single electron fashion with the alkene, generating this new carbon radical and a carbon halogen bond. Well, the process here, you can see from an enthalpic perspective, HCl and HBr have favorable delta H's for the formation of this new carbon halogen bond, whereas HI does not. The iodine addition is actually an unfavorable addition enthalpically. Overall, all of these entropy terms are unfavorable, right? So, because if you think about it, we have two molecules here coming together to form one molecule on the right-hand side. So entropy is very unfavorable in this reaction. So for the first step, HCl and HBr are a favorable process, HI not so much. Now looking at the second propagation step in the process, right, this is the product forming step. We are, again, performing another hydrogen abstraction, right? The radical of the carbons reacting with the hydrogen of the HX bond, form a new carbon-hydrogen bond, and generate another halogen radical. Well, in this case, we look at the enthalpy the enthalpy term for each of these, and you can see from an enthalpic perspective now HBr and HR are favorable, whereas HCl is unfavorable. And the reason for that is the chlorine radical that is generated is unstable. It's not a stable radical. Entropy in this reaction overall is approximately equal to 0, right? Because we're going from 2 molecules on the left to 2 molecules on the right. So overall net neutral entropy term. But you can see now from the perspective here, HBr and HI are favored in step 2. So if you were to think about this overall process, that in the first step, HCl works great, but in the second step, HCl does not. So you have an overall, moderate reaction of HCl via peroxide mechanism. HI, unfavorable in the first step, favorable in the second step. Again, a similar, overall unfavorable process because of, one step being unfavorable. Whereas HBr wins out because it's favorable in both the first propagation and second propagation steps. All right, so if we look at the addition stereochemistry that's going on here, when we add HBr across a carbon-carbon bond and under a peroxide mechanism, just like we do with the reaction of HBr in a non-peroxide mechanism, we have the ability to form a new chiral center. Right, so this reaction here, you can see a new chiral center has been generated because we have a carbon atom, a bromine atom, a hydrogen atom, and another alkyl group, in this case bound to it. So 4 different groups, so a chiral center has been generated. If we didn't start with a chiral molecule, as we haven't here, then you're going to generate a racemic mixture, right? All that means is we have a 50-50 mixture of both the S and the R isomers at the center. And this key here is because the molecule that we're working with has only one chiral center. If we have, a stereocenter present in the molecule, then we can actually get a mixture of diastereomers that are going to be obtained. Well, that means if you think about it, if this carbon atom here, for example, were chiral, it had 4 different substituents, then that carbon atom over here on the left-hand side is also going to be chiral. So we have, both, perhaps the S isomer. Let's just arbitrarily label this S. So therefore we would have both an SS isomer and an SR isomer. So we would generate a mixture of diastereomers as products, right? Because one would be the SS enantiomer, the other one would be the SR enantiomer, right? These are not, excuse me, I misspoke. The SS diastereomer and the SR diastereomer, right? These are not enantiomers of one another, right? Not enantiomers of one another. They're going to be diastereomers of one another because of the fact that you have a chiral center present. So that's one of those interesting facts when it comes to, any type of radical addition chemistry. If you start with a chiral molecule, you generate a diastereomer mixture of 2 molecules out as products. And fortunately, the advantage to that is since they're diastereomers, they're easier to separate than enantiomers would be. So many radical reactions are used for polymerizations. Lots of the polymers that exist in society are generated via free radical chemistry. All that polymerization is a process that joins together many small units called monomers in a long chain. We've talked about polymerization before in the past, right? And we talked about it in particular, the reaction with ethylene, and we were talking about it under both cationic, I believe, and maybe anionic conditions. Now, under radical conditions, we can also generate, ethylene, to convert ethylene into polyethylene, the polymer, as well, right? All we're talking about, we have carbon 1, carbon 2, and that carbon 1, carbon 2 repeat happens over and over again, and depending on the conditions as to how many polymeric units couple in the end. So these steps should look very similar to all the previous ones that we've worked through. We have our initiation step, again, where our initiation occurs, where we have a homolytic cleavage of the peroxide generating two peroxy radicals or alkoxy radicals. That alkoxy radical then performs an addition reaction, right, with the alkene, forming this new carbon-oxygen bond and the radical. Now, recognize this, and this is all part of the initiation. Even though we reacted with one molecule here in the very first step of ethylene, we are still just initiating the reaction. And this will make more sense as we look at the propagation steps on the next slide. Oh, and before I do so, I just want to stop and remind you, because people tend to frequently forget, right, when we're talking about the R groups here for the peroxides, right? A peroxide, that R group is equal to pretty much any carbon atom, and right, any carbon compound. It can be, I've shown you examples with tert butyl hydroperoxide. We've given you examples with the acetyl hydroperoxide. Right, so the R groups just recognize that these the alkoxy radicals that are generated can have any number of R groups present on them. So when we're discussing radical polymerizations, they're usually going to proceed via a radical chain mechanism, right? So when we look at the propagations, the very first step is an addition step. And you can see here where the initiator that was generated on the previous slide now reacts with a new molecule of ethylene, forming a new carbon-carbon bond. That new carbon radical that's generated reacts with another ethylene molecule, generating a new carbon-carbon bond and another radical, which adds to another ethylene molecule. And the process obviously repeats over and over again, eventually making a molecule large enough that we call it a polymer. Right, so this basically the summation of the propagation steps and gives the overall net reaction, right, for this particular sequence, and basically the number of times that we react determines how long these polymeric chains get. The reactions aren't perfectly clean. You frequently get some that are polymer chains that are longer than others. Some are shorter, because as these molecules grow and get larger and larger and larger, they get intertangled and they can't necessarily reach new ethylene molecules, and they just kind of float around until the reaction terminates. So as I mentioned on the previous slide, once the chains get large enough, they need to be capped or essentially terminated, because otherwise they just hang out there as radicals. If they have nothing to react with, they'll react with neighboring carbon-hydrogen bonds. And you can see here the termination reaction is just essentially another coupling reaction One of the possible pathways is reacting with another alkoxy radical, forming a new carbon-oxygen bond at the end. They could couple between two different polymeric chains, right? Those making a much, much larger polymeric chain. Again, coupling reactions are the termination processes that are occurring here. One of the uncontrollable processes occurring under polymerization is chain branching. It's basically one of these inevitable events that occur in the process. And what's happening is, right, we have the radical that is generated through the propagation steps, and occasionally that radical will react with a CH in the middle of another polymeric chain. Once that happens, we generate a new radical that is found somewhere in the middle of the chain, which can then react with ethylene molecules in this case and start growing a chain off of the side of the original polymer. And that chain we call a branch, right? Because it's not on the original chain that was propagated. So branching occurs, and it's frequently desired, and the chemists are able to tweak the amount of ethylene and initiator in the process in order to create more or less branching. And it's desired in some cases because highly branched polyethylene forms basically flexible plastics, right? You think about a squeeze bottle, those are polyethylene that are flexible, whereas unbranched polyethylene is usually very brittle and rigid. It's kind of like a plastic bottle cap, right? You have much harder plastics. You don't want your plastic bottle cap to be soft and flexible because you want it to be able to hold the water in your container. Ethylene derivatives are polymerized for varied purposes. We've talked about some of them before, and the key is right, we change some of the substituents on ethylene to give us different properties, and you can see here if we use propylene, which contains a methyl group, we can generate polypropylene, right? The repeating process just generates now a methyl group in the polymer. Polypropylene is used in carpet fibers, it's used in appliances, it's used in car tires, so many diverse uses for polypropylene. Part of it has to do how long you make the polypropylene chains, give you different overall strengths and feels to the plastic that's produced, or the polymer that's produced out in the end, so you can generate different length polymers for different overall purposes with different branchings and the like. Polystyrene is made from styrene, right? If you recall what that pH stands for, it's a phenyl group. Right? That phenyl group is a very large group of 6 carbons. So polystyrene has a giant phenyl group present. It's used in televisions, it's used in radios. What we're probably most familiar with is its use in styrofoam. You can see, styrofoam is nice, light and fluffy. Obviously, the uses in televisions and radios is not going to be the same. So slightly different polymer chain lengths, perhaps more or less branching, will give you the different properties that you observe for each of the different versions of polystyrene that are being used. Interesting side fact, styrofoam, in regards to styrofoam, there are some scientists who are working with beetle larvae, and they discovered that the beetle larvae will actually eat styrofoam. They consume styrofoam. All they have to do is keep the styrofoam wet with a little bit of spray, keep it misted, and the beetle larvae are able to live for weeks on end consuming styrofoam, and they produce beetle larvae manure, which scientists then use to grow plants. So there's some work obviously being done as a way to recycle our current styrofoam, because I don't believe there are any current methods for recycling styrofoam, and turning your styrofoam into manures, which you can then perhaps grow your next set of vegetables in. So some additional ethylene derivatives. If we start with vinyl chloride, right, where the biggest difference here is now we have a chlorine atom added, we end up forming polyvinyl chloride, right? The repeating chlorine atom in there. We've talked about this before, right? It's PVC. It's used for piping, for plumbing. It's used in CDs. It's used in garden hoses, raincoats, shower curtains. Right? PVC is extremely durable material from very hard, almost brittle type substances like in the plumbing to very flexible substances like in shower curtains and raincoats and hoses. So you can see, again, varying chain lengths, varying ability to have cross-linked chains will give you the different properties that you observe for the various types of PVC. One that we probably all are very familiar with, but weren't familiar with what it was made from, is if we start with tetrafluoroethylene, we make Teflon, right? Any of your pans that might be coated in Teflon, right, have fluorine atoms all up and down the carbon backbone. And basically that nonstick coating is nonstick because of the hydrophobic fluorine atoms that are coating the entire polymer surface. And that's the key for any type of nonstick cooking surface that's coated in Teflon. So in the petroleum world, radical processes are used all the time. And in particular, in the reverse process, right? Well, the cracking of hydrocarbons is actually a radical process, right? Where we're instead producing smaller alkanes from larger alkanes. So the exact opposite of polymerization, where again, the cracking process you can see is shown here. We are splitting this carbon-carbon bond. One of the electrons is moving to the left-hand side to form a new radical. The other electron is reacting with a radical that was generated via some type of initiator and forms a much smaller propylene derivative. Again, this is one way of generating propylene, which then will allow you to create polypropylene, of the desired length and size, in polymerization reactions. So this is one of the major ways that we generate all of our starting materials for many types of chemical syntheses. Hydrocracking, right? It's the similar process. It's just done in the presence of hydrogen gas, and it forms only alkane products, right? So this splitting that occurs generating, instead of propylene, it forms propane, right? So it's a way of creating propane. Again, this is a radical-based mechanism. We're not showing the mechanism, a little bit more complex here. But we generate propane. That propane can then be separated out from the other varying length chains and gives us the ability to then bottle it. And you can then use it on your weekends for cooking up your burgers and dogs. So they also have reforming processes that occur in this mixture where under desired conditions, you have a radical process which produces branched alkanes, right? So you might want to take your long straight chain branched alkanes, you can heat them up to certain temperatures, create your varied branched alkanes that again are going to have different properties than the original non-branched alkanes. So again, radical processes are extremely useful, especially in the petroleum industry. So we've discussed this radical halogenation process. How useful is it? What is the synthetic utility of this halogenation process? Is there a difference of chlorine versus bromine? So when we think of chlorination, we discussed about how those chlorination reactions were not very selective, right? You ended up with, what was it, a 1 to 1.2 to 1.4 ratio, primary, secondary, tertiary. So when you're synthesizing alkyl chlorides, if you have a substance that is going to generate varying types of radicals then chlorination is going to be very useful. But if you start with a starting material that can only produce one product, then that chlorination product can be generated very easily and cleanly. So again, this cyclohexane is perfectly symmetrical. Every single carbon has two hydrogens present, all secondary all the way around. Where you want to use bromination is where you have varied types of substituents, because it's a much slower process, it's more selective, and you can have the ability to form several different monohalogenation products with chlorine. But if we use bromine, bromine is going to be selective for this tertiary center for halogenation. So that's the key. We can be very selective with what we can synthesize with bromine versus chlorine. So if we look at the synthetic utility of this halogenation reaction, right, we want to functionalize alkanes. Right, so the key here is we start with an alkane, we can functionalize an otherwise unreactive alkane, which then can be converted into other useful functional groups. This is the key, right? We have methyl cyclohexane. There's nothing much we can do with methyl cyclohexane other than use it as a solvent for cleaning materials or burning it as kind of a petroleum type fuel. But react it with NBS, we can react exclusively at, or nearly exclusively at, the tertiary center, generate the tertiary bromide. We can then take this tertiary bromide, use a substitution reaction where we replace the bromide with any number of groups. Right, we've talked about any number of SN1, SN2 type products that we can generate via the tertiary bromide. Oh, sorry, I should say not SN2, only SN1 processes to generate the substitution products. We can also eliminate the bromide, form either the Zaitsev more substituted carbon-carbon double bond, or maybe even the Hoffman less substituted carbon-carbon double bond, and we can take those alkenes and further derivatize them down the line. So let's wrap up this chapter with a review of the reactions that we've covered. Right? Overall, these radical reactions are very synthetically useful. We can apply them in multi-step syntheses throughout the entire text or the course. We learned about the anti-Markovnikov addition of HBr to alkenes. Right? We take the alkene, HBr, and a peroxide gives us the anti-Markovnikov addition of HBr across the carbon-carbon double bond. We learned about the reaction of NBS with light to give us the allylic addition products. You can see here, right, where we have two different allylic positions here. In this case, symmetrical molecule gives us the allylic bromides as products. And then we also discussed the bromination of alkanes, again, as another synthetically useful process where we take and can select for tertiary centers over primary centers when we react with bromine and light to give us the very synthetically useful tertiary bromide, which can then again undergo multiple different steps into the future. So we're going to end here, end of the chapter, and we'll move on to chapter 11, beginning following in the first day of class during Thanksgiving week. Have a good weekend, everyone.